with lines, and they'll just kind of give you a formula. But, yeah, I don't know. Formulas are hard to, I think, memorize without some sort of knowledge of why stuff works the way it does. Okay? So, at the moment, what you need to be able to do is to parametrize circles, sort of ellipses, and then also along functions. Keep in mind, I'll tell you which problems to look at in the book. Some of these problems are going to be provide a parametrization. You go looking in the back of the book for the answer, and it's not your answer. That doesn't mean what you have is wrong. So you know, in other words, there's infinitely many different possibilities for answers. So if you're getting stuff and you need to see it, make sure that what you've done is right. One thing you can do is ask in class, okay? Your calculator has the capacity to do these graphs, at least up to a point, in 2 dimensions. And I haven't done anything that's 3-dimensional. So if in your calculator you go to mode, and I can't quite remember, I don't know if it's equation or function, that's what they do. Okay, so function, parametric, and then there'll be polar. If you switch the mode to parametric, and then you hit y equals on your calculator, and then you hit that key, instead of what you get in the function mode, where you get y1 equals y2 equals, etc., what you'll get is this. The 1 meaning first curve, and then there'll be an x2t, etc. When you put this in, you can also go to your viewing window. And when you go to the viewing window, you can both set the parameters for x and y, you know, to get your screen, but you can also set the parameters on t. This is especially helpful with the circles. Because as you enter stuff in, if you look, for instance, at cosine of t, sine of t, when you enter this in, you will see the way the circle goes in, it's going to be oriented counterclockwise. But if you should enter in negative cosine and positive sine, you'll see your curve begin over here and go in this direction. So in other words, when you look at what the curve comes to, you will both get where it's starting and the orientation. Now, I think you'd have to check default, because when I say starting, I'm saying t equals 0. And you can set t to have a minimum of -5 and a maximum of 2 pi if you want. It'll start it where you tell it to, it'll end it where you tell it to. But if you get confused with directions of the rotation, etc., calculator is going to give you a reasonable chance. Okay? second comment about this is most things you cannot graph. So you take pre-calculus and you do all these graphs of exponential, log functions, trig functions, rational functions, square roots, cube roots. You do all this stuff, and all somebody has to do is write down a polynomial like the following. And say, graph it. It's just a polynomial. And you can't. Okay? I can't even tell you where this crosses the x-axis. I can't look at my calculator and get a picture of the graph, at least not of the whole graph. I can tell you some things about it. I can tell you because that's an even degree and that's positive, that eventually it will go up on both ends. I can tell you that the maximum number of x-intercepts is 10, but if you find 8, maybe you spend the rest of your life looking for the other 2 and maybe they don't exist. Nobody asks you to graph this. A calculator, which I'm never real fond of because there's far better graphing programs on computers, but you can get somewhat of a feel for a certain range of that graph. The point I'm trying to bring up is nobody's going to ask you to graph this. They're going to ask you to graph things that you can get a reasonable picture of, basically without a calculator even. And they do that, work on the graphing so that you have reasonably good examples to work with. All right? If I said x is t cubed plus 54t squared and y is 7t to the 1/3 minus 58t to the 3/5 plus 1, I have no idea what that shape is going to be. A calculator will give me maybe a reasonable sketch, if I'm lucky, for certain values of t. Nobody's going to expect you to do that. Okay? What you're looking for are some reasonable examples so that when the time comes, I can pull them up and we can understand what you can learn from the pictures and understand where the pictures come from. Okay? That's why when it comes to the parameterizations, there are certain standard examples which are completely within our ability to write down. From functions, they're real easy. Circles, easy. Parabolas, a little bit stickier, but not too bad. And then lines are going to be also very easy. I'm just not going to explain them at the moment. Okay? There will be problems where the book might go x is 3t and y is e to the 9t squared, and they ask you, what does this parametrize? So this parametrizes along the curve. Y is e to the 3x squared. Is it 3x squared or 9x squared? 3x squared. Yeah. Simply y e to the x squared, not 3x squared. because when I square this, I get that. Okay? When the book is asking you to do that, there should be some fairly straightforward ways of seeing what those relationships are. Algebraic relationships or the trig relationships between the functions. Okay? These are good problems, but the things that I really need you to be able to do is to provide the parameterizations, because there will be problems towards the end of the semester where you're going to have to go crank, crank, crank with them. And these examples are going to be the ones they work with. Okay. I should also mention that you can have parameterizations in 3 dimensions, and in fact, that will happen an awful lot. Most of the time, you can't get a reasonably good graph. Every once in a while, you get ones that you can. So, for instance, this is going to give you a spiral like this, which is supposed to have the same diameter. What I'm seeing is that x squared plus y squared is a circle. And then what this z is, at various points, it's lifting or dropping that corresponding point on the circle down. Okay? I'm not going to be asking you to graph these things, so, you know, there are some nice exercises, and we'll probably look at them on Thursday, where they give you some of these curves. I think they have some of these. And they ask you, well, they don't do too many, I guess. But I think there are some where they'll ask you, you know, match up the formula to the curve. Those are always instructive to look at. But in point of fact, I mean, I'm not going to ask you to sketch something like this. Most of the time you can. And then unless you've got a calculator that does stuff in 3 dimensions, forget about it. Okay? Okay. Before we start into the vector stuff, let me briefly mention the 3-dimensional system that we'll be looking at. So this is the Cartesian Coordinate system, and we will also be looking at 2 more coordinate systems, cylindrical and spherical. But for some time we'll stick with the Cartesian coordinate system. And the way in which we orient this is going to be, and I apologize, different than how a lot of you guys have seen it in your engineering classes. It's just rotated differently. And for me to comply with your engineering orientation, then everything in the book is screwy. I'm just going to stick with what not only this book, but just about all math books do. And that is x-axis. Positive x-axis is going to come out of the page, as opposed, I think, to the z-axis in your engineering guides. The y-axis is going to be in the page, and the z is going to go up and down also in the page. And I think the orientation is going to look like that because typically when we look at functions of more than one variable, we'll be writing functions like this. And we'll think of z as being the dependent variable, dependent on x and y. I think that that's going to be the reason why they orient like this. So that the question will be, above the XY plane or below. So if I go in Cartesian coordinates to plot a point along here, positive X comes out from the page, positive Y goes to the right, and positive Z is up above. And if I went to plot a point 1, 2, 3, then I would come 1 unit in the X direction. I would go 2 units along the Y. This point down here would be the point 1, 2, 0. And then I would pull it up 3 units, and this would be the point 1, 2, 3. Okay. There will be other ways of looking at these points. We'll have 2 other systems, but not till we get to the integration. All right. Now, we're going to spend more time working in the 3 dimensions, but we are not going to do that right now. I just bring this up now because the book makes a distinction when they begin chapter 12 between vectors in 2 dimensions and vectors in 3 dimensions. I'm just going to do them both at once because there's not really any difference. So I'm not going to finish through this section, but I'll begin sections 12.1 and 12.2. So these are going to be vectors in 2 and 3 dimensions. Okay. Vectors get covered in a whole bunch of places. You'll see them introduced in physics classes. You'll see them introduced in your engineering classes. You'll see them in a Calc 3. Pre-calc, for that matter, will do a little bit. And when you look at them yet again in linear algebra, at least certainly in the 3-hour linear algebra that a lot of you guys have to take, you'll get a whole nother introduction in a much more abstract setting. Everybody's got their own way of looking at it. And I'm going to look at things through the math perspective. Doesn't matter what the perspective is, they amount to the same things. Your computations are going to be the same. But you're going to be maybe asked to do different things depending on which class you're looking at. So, from my point of view, a vector is any quantity. I hate to say quantity because that to me sounds like a number, and a vector is more than a number. So a vector is anything that requires both of the following to completely describe. One, magnitude. 2, direction. Anything that, in order to give a complete description of, you need both of these, is a vector. Examples. Velocity. You have in your car a speedometer. which tells you your speed. It does not tell you the direction in which you're moving. You can go 10 miles an hour forward, you can go 10 miles an hour while you're backing up. The only way you can tell the difference is to look out the window. Okay? Now, if you've got a compass and you put that compass in conjunction with your speedometer, then you've got a measurement of velocity. When you work with velocity in Calc 1 and Calc 2, the distinction of direction is very simple. It's always motion in a straight line, plus means you're going in the positive direction, minus means you're going in the negative direction. Frame of reference tells me what's positive and what's negative. But what we're going to be doing here is allowing motion to be all kinds of directions, within 2 dimensions or even within 3. Okay? So there's a difference between saying I'm traveling 10 miles an hour or 70 miles an hour versus saying I'm traveling 70 miles an hour due west. All right? And when I put that direction in with the magnitude, that's an example of a velocity. Wind speed. Same deal. I can say the wind is blowing 30 miles an hour. That's a magnitude. I can say it's blowing 30 miles an hour and coming out of the southwest. That's a vector. You've got direction along with magnitude. And something that's very, very similar would be fluid flows. Water moving down a river or down a pipe has got both a direction and a magnitude. Okay? So these are very, very typical examples of vectors. Nice real world examples. Okay? We use, well, if I want to talk about a vector, I'll write one of the following. I'll write a letter and I'll put an arrow over it. Make it a full arrow if you want. I tend to do half arrows. Or fold. Like that. Well, obviously, I'm not going to do this every time I write down a vector. This is what you'll see in the text. This is what you'll see when you're reading a paper. Okay? So this is printed, bold, but if you're not doing that, or if there's any question at all of what you are working with, then you put that arrow over the top. Okay, now's my time to kind of warn you guys. Teachers have their own quirky little things. If you write this, I am not going to treat that as a vector. In fact, this is going to represent a number. Which we will call a scalar. intend this to be a vector, you've got to put the arrow over it. Do not assume I can mind read. If you want me to mind read and believe that there really is an arrow and that this is really a vector and it's what you intended, if you give me that power, I'll take that power. And then when you write something down that's the correct answer, I'll say, well, you didn't really mean that. You know, you don't want me to do that, okay? Don't give me that power. So what I will do is I will read what you write and not read anything into it. I'll not pretend that you really meant this when you wrote that. Habits count for an awful lot. You can't go into the gym and shoot a free throw, make it, and say, okay, I can do this. And then figure you're going to go out and shoot them all correct, especially not the crowd there watching. You know, it just doesn't work. You can't play something on a musical instrument correct once and then say, I'm done, I know how to do this. I mean, it's just ridiculous. Our brains are basically feeble. They require a certain amount of drill. What you do in practice is what you do in the game. That's as true of math as it is of anything else I know of. If when you're doing the homework you're sloppy, then when you get on the exam you're going to be sloppy. I very seldom, if ever, have ever seen anybody do stuff wrong in their scratch work, in their practice, and then come in and instantly have everything being perfect on the exam. You know, I can't go home and make sure you're writing everything down. That's a personal decision you make. But I'm a stickler on notation, and if you write this when you mean that, I'm going to take it to mean this. I've seen too many people get mixed up down the road because they start treating things as vectors which are not vectors. And that is a road that just takes you down the wrong path. I mean, it just is a mess. That's not just true here, it's true in any classes outside of here. It's basically true in anything you choose to do in life. But notation, this gets read as a scalar, this gets read as a vector. To further confuse issues, force is a vector, and frequently they will say this is a vector with magnitude, and they'll use the same letter without the arrow over it to indicate the magnitude. So force has a magnitude. I apply a force of so many newtons to something. It's got a magnitude, but it's also got a direction. So if I apply a force of 100 newtons to this desk, will I move it out the door? Well, it depends on what direction I'm applying that force. If I apply it straight down, it's not going out that door. You know, it's got those two aspects to it. Magnitude, direction. And for people to keep track of, so that people don't get confused, they will use the same letter without an arrow or not in bold if you're reading it in something that's been printed out to represent the magnitude of a vector. So you won't see that at first, but down the road in here you will. So you will see velocity as being this, and this will be speed, the magnitude of the velocity, and it helps you to keep track of stuff. okay? So this is how I denote the vector. We draw vectors in this way. So this is the way we visualize them. We draw an arrow. The arrow indicates the direction in which that vector is pointing, and its length corresponds to magnitude. If I take this arrow and I pick it up, and to the best of my ability, I draw the arrow that's pointing in exactly the same direction and has exactly the same length, these represent the same vector. So vectors can be picked up and moved all over as long as you don't vary direction or magnitude. The picture represents the same vector. You can think about it like current of water moving down a river or wind. It doesn't start at a specific place. You can think about it as being all around, but it's all moving in a particular direction with a particular magnitude. So he gets picked up, moves all over. What the arrow basically represents is displacement. So it's not nailed down at a particular spot, but it's going to indicate the amount of displacement in the X, Y, and possibly Z directions. Okay? Now, I'm just doing this with pictures right now. When we come back on Thursday, I'll start moving into doing this with the symbols representing with numbers. But when I have a vector, I can multiply that vector by a scalar. So scalars are numbers. And I can multiply a vector by a scalar. So for instance, if this is the vector W, to the best of my ability, this would be the vector 2W. It should be in the same direction, but twice as long. And if I wanted to look at 1/2 W, it would point in the same direction, but half as long. If I draw the vector in with the same length, parallel to W, but pointing in the opposite direction, I would call that vector minus W. So I could look at minus 2W. It would double the length of my vector and point it in the opposite direction. Okay? So visually, this is how we look at multiplying a vector by a number or by a scalar. I can add two vectors. No, this is still just visual. So if I have this vector, say v, and this vector, let's call it w, if I want v plus w, what I'm going to do is to pick up one of these two vectors and place its tail on the head of the remaining vector. Doesn't matter what you work from. So what I'll do is redraw my vectors head to tail. So if I did this, let me see, this is V, I could pick up W and I would put its tail on the head of V. V plus W is the vector starting at the open tail, ending at the open head. Okay, so I'm going to leave this picture up because it's notes. But what I would have here, so this would be V, this is W. This right here is V plus W. So, well, okay, I'll comment on this, but let me remark that had I done this in the opposite way, had I looked at W, which is here, and placed the tail of V onto the head of W, then I would draw V plus W like this. And boy, these sure don't look the same, but that's because I've got these lengths probably somewhat different. Okay? But these guys should be the same. Okay? Alright. This is a test question. I mean, I'll be able to tell you some things that will be on tests. I will give you V and W and ask you to draw V plus W. If you draw this, this is wrong. And I mean, I'm only telling you this stuff from experience because I've gotten this stuff on tests. If you draw this, that's wrong because there's no arrow, there's no direction given. So if you're asked draw V plus W, you've got to draw it, don't leave it set up like this, and you've got to give a direction. Okay, I'm gonna have to post homework up on the website, but in section 11.1, one, 5, and then 7 through 17 odd. Give you a line, yeah. Okay, and okay, so there's a few others. 25. Trying to avoid here the lines. 35. They don't give you an orientation. It's a circle, but there's no orientation. 41. That should be enough, I think. Yeah, there are problems that you may have questions. We'll start off Thursday going over questions. Okay. And I'm just kind of clicking through these.